Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is Week 2, Part 1. Today, we're diving into the mathematical engine of deep learning, backpropagation. It really is the single, elegant algorithm that allows a neural network to learn from its mistakes. Understanding it is absolutely the key to unlocking how modern AI truly works. So the central challenge in deep learning is one of truly staggering scale. I want you to imagine a control panel with billions, maybe even trillions of tiny little dials. These are the network's parameters, or its weights. Our goal is to tune every single one of them just perfectly to minimize the network's error. So the question is, how on earth can we orchestrate such a monumental task efficiently? Well, the goal is to find the gradient. That's the direction of steepest error. So we can then nudge the parameters in the opposite direction. A naive approach, the one you might think of first, would be to just poke each parameter one by one and see how the error changes. But as you can see from the complexity on the slide, O of W squared, the cost of this method just explodes quadratically. For a billion parameter model, it's not just slow, it is computationally impossible. This is where backpropagation comes in. With a linear complexity of O of W, it computes the exact gradients for all parameters in a single, incredibly efficient pass. The cost scales with the number of parameters, not its square. This chart really puts that efficiency gain into perspective, doesn't it? The difference between quadratic and linear complexity, it isn't just a small improvement. It's the fundamental algorithmic leap that makes modern deep learning practical. Without this, the AI revolution as we know it simply wouldn't exist. So how does backpropagation pull off this incredible feat? Well, the magic lies in two core mathematical tools. First, viewing computations as graphs, and then wielding the chain rule of calculus to navigate through them. Right, so any complex mathematical expression, no matter how scary it looks, can be broken down into a computational graph, where each node is just a simple operation. This turns a huge calculation into small, manageable steps. And on the right, we have the chain rule, which is our recipe for finding derivatives through these steps. Now, the scalar version is simple, but the multivariate rule is the real key for us. It tells us to find the total influence on a variable by, and this is the important part, summing up the contributions from every single path that leads to it. This idea of summing up influences is absolutely central to how backpropagation works. The algorithmic application of this chain rule on graphs is called automatic differentiation, or AD for short. And there are two main flavors. You've got forward mode AD, which is efficient when you have just a few inputs and many outputs. But that's not our scenario, is it? In deep learning, we have millions of inputs, all the weights, and only one single output, the final scalar loss. This is where reverse mode AD, which is precisely what backpropagation is, becomes so crucial. It's perfectly suited to compute gradients for all of those inputs in just one backward pass. Now, this incredible efficiency doesn't come for free, of course not. There's a fundamental trade-off at play here. To make that backward pass so fast, we absolutely must store, or cache, all the intermediate values that we calculated during the forward pass. So in essence, we trade a significant amount of memory to gain an enormous amount of computational speed. We've covered the theory, now let's make it a bit more tangible. By walking through a simple example, we can build a really solid intuition for how these gradients actually flow backward through the graph. Okay, here on the slide, we have a simple function. F equals the sum of x and y, all multiplied by z. With our inputs, the forward pass is really straightforward. X, which is -2, and y, which is 5, are added to get an intermediate value q of 3. Then q equals 3 is multiplied by z equals -4, giving a final output of -12. The most critical step here, the one you can't forget, is that we cache these intermediate values. We're going to need them for the backward pass. And now for the backward pass. We always start at the very end with an initial upstream gradient of 1. At the multiplication gate, the chain rule tells us to multiply this upstream gradient by the local gradient of that gate. For a multiply gate, the local gradient for one input is just the value of the other input. So the gradient flowing back to q is 1 times z, which is -4. The gradient for z is 1 times q, which is 3. Okay, now we reach the addition gate. Its local gradient is always 1, so it just acts as a simple distributor, passing the upstream gradient of -4 back to both x and y. And there we have it, our final gradients are all calculated. What we just did intuitively has a formal name that lets it scale up to entire layers of a network. A Jacobian is a big matrix containing all the partial derivatives for a function. For a neural network layer, this would be enormous, just impossibly large to store. But here's the crucial insight. We never actually have to build it. Instead, backpropagation cleverly computes something called a vector Jacobian product, or VJP. As you see on the slide, this operation takes the upstream gradient vector and efficiently multiplies it by the local Jacobian to produce the downstream gradient, all without ever forming that massive matrix. It is the engine that powers the backward pass. We've built the intuition with a simple example. Now let's scale this concept up and see how it generalizes to a full layer within a deep neural network. To scale this up, we need to introduce a key quantity, the error signal, denoted by the Greek letter delta. As the equation here shows, delta at a given layer L is the partial derivative of the final loss E with respect to the pre-activation input Z of that same layer. You can think of it as the core currency of backpropagation. It's a single value for each neuron that tells us exactly how much that neuron's input needs to change to reduce the final error. It's the blame signal. And here we have the heart of the algorithm, the backward recurrence formula. This elegant equation tells us how to calculate the error delta at any layer L, given the delta from the layer ahead of it L+1. Let's break it down. The equation says delta L equals the transpose of the weight matrix W multiplied by delta at L+1, and that result is then multiplied element-wise by the derivative of the activation function H'. So first, we take the error from the next layer, delta L+1, and propagate it backward through the weights using the transposed weight matrix. That's our vector Jacobian product in action. Then we multiply that result by the local gradient of our activation function. This acts like a little gate, controlling how much error flows through each neuron. This single formula is just applied recursively, layer by layer, from the very output all the way back to the input. So, the hard work is in calculating these delta signals. But what's the payoff? Well, once we have the error signal delta for a layer, calculating the gradients for its parameters is immediate. As you can see from the formulas, the bias gradient is simply the error signal itself. The weight gradient is found by taking the outer product of that error signal and the activations from the previous layer. This makes perfect intuitive sense. A weight's contribution to the final error is proportional to both the error signal at its destination neuron and the activation signal that passed right through it. All right, let's circle back to our original problem of efficiency and look at the practical implications of this entire process when we're training large-scale models in the real world. While the backward pass is computationally heavier than the forward pass, often by a factor of about 2, as the chart suggests, the overall time complexity remains linear, which is perfectly manageable. The true practical bottleneck for training modern deep learning models isn't time, it's space complexity. Remember that trade-off? We have to cache all those intermediate activations. This memory cost scales directly with the network's depth and the batch size, and it is the primary reason that training a model requires vastly more GPU memory than just running inference with. So, to summarize the entire mechanics of learning that we've covered. 1. The structural view. Neural networks are basically just big computational graphs. 2. The mathematical foundation. Backpropagation is a clever application of the chain rule known as reverse mode automatic differentiation. 3. The algorithm itself. We cache forward values, then compute local gradients and propagate the error signal backward through the graph. And 4, the result, an incredibly efficient algorithm that gives us the exact gradients from millions of parameters in linear time. So, we've now built the entire machinery to compute the gradient for every single parameter in the network, and to do so with remarkable efficiency. But this leaves us with a final, crucial question. Now that we have the direction of steepest descent, what do we do with it? How exactly should we use these gradients to update our weights and navigate the complex loss landscape to find that minimum? Well, that is the science of optimization, and it's exactly where we'll pick things up in part 2.